Best experience ever. Literally, they were hard to do. No, all like.
All right. Okay. So sorry guys. Yeah. So I was waiting for the bus and never came, so I ended up walking. And so, well, it came, but it was just like going in the other direction, all of them, all four of them in a row. I think there's a mistake. Yeah. Okay, so you should see my office hours. So we start today. So today's office hours is at 6. It turned out that there were some people who preferred a later time, so I honored that for those people. And you can come in, and they're all in Clements. So I'm sorry they're all like different rooms because I couldn't get it to be the same room for all of them. Because I don't use my office because I share an office with some another person, and it's just really, really small in there, and it's not going to fit. Like probably only like 2 or 3 people can only fit in there. So I reserved these classrooms for the whole semester, but they're different each day. So just keep them. I mean, the good thing is that I made them all Clements. So if you end up like being in the wrong room, you're at least in the right building. And it's hybrid, so you can also join by Zoom. This is the Zoom link. And all of it's on this Google Calendar. So like this is like the appointments link. You just click on 30 minutes or 1 hour on the top if you want to book an appointment. But there is also a Google Calendar down here, and it lists all the office hours. So the regular office hours has this like blue little like circle. And there's like one here, one on Wednesday, and one on Friday. And then all the TA help sessions. This is the graduate TA help sessions are has like a picture of some person in front of a board. And you should go to the one that says Math 3313. There's 3 of those. They're on Tuesday, Wednesdays, and Thursday. And you may find that I post some extra office hours. This usually is when another student or a couple of other students in the class requested to meet with me. I kind of decide often if they don't ask it to be one-on-one, I usually publish it so that everybody can come. And this also is hybrid. The location would be listed. It says Clements 224. That's today, right after our class. And then you could also join by Zoom. And if you wanted to subscribe to this calendar, you just click on this plus Google Calendar down here, and it'll go and add it to your Google Calendar. And you can always unsubscribe. You can always hide it too. I think like you can have all these calendars in your Google Calendar. You can just like use a check mark to like hide it if you feel like it's annoying. So if you subscribe, then you'll see like these extra office hours pop up like automatically. And so you can just like wake up in the morning and be like, there's another one that I can go to. And so that's available. So and I try to make sure from everybody's responses that there's at least one office hour that people can attend per week, but feel free and don't hesitate to schedule. You just click on 30 minutes or an hour up here, and then you just like you select the time and you type your name and then specify whether you want it to be Zoom or whatever. And so definitely feel free to do that. And then if you don't say you want it to be one-on-one, then I probably will put it on the calendar here so other people might join as well. So, but somebody has to request it before I can post it as an extra office hour. Any questions? Okay, so let's continue where we left off. So we are basically going to finish separable equations. The idea of a separable equation is something that you can write as a product purely in terms of x and purely in terms of y, so that you can separate everything. So that means you just shove, like this was the one that we ended up finishing with. So that, well, this one was just in terms of x on the right, and so you can just divide both sides by the right-hand side. and you would have successfully written everything with x and dx on one side and everything with dt on the other side. So this one was an extreme example where you just had only a function of x on the right, so you just divided by it. And then multiplied by dt, and you just have dx over x squared minus 2x equals dt. Those are successfully separated. And so you just end up taking the integral of both sides. Of course, the the integral of the right-hand side is super easy, but this left-hand side was an exercise in reviewing your partial fractions. So you can do that. And then I warned about like there's always going to be like a c. Remember, like a differential equation is morally, it's like the spirit of it is basically you're going to eventually anti-differentiate. So you're trying to find the x that would satisfy this differential equation, and there's going to be some antiderivative involved. And whenever you do that, there's going to be an integration constant c. And so your general solution, now if there's an initial condition, then you can plug that in to find what your c is. But if there is an initial condition, then there's always going to be like a c somewhere. But where it appears is not just random. So the c appears as soon as you take an antiderivative, and then you're going to do a bunch of algebra to solve for x, but you got to make sure that the c is there before you do all the algebra. Then that means the c might end up somewhere, like in this problem, it ends up being in the denominator in front of the exponential term. So I wrote a little thing here saying don't add c late. So like don't just add it later. So this is wrong. You can't do 2 over 1 minus e to the 2t plus c. The c actually is in front of the e there, and that came out because the c ended up showing up at this stage, not later. So keep that in mind. And just delete this as well. Okay, so let's do one more, and then we'll be done with the separation. So this one, you can also see that on the right-hand side, it's a function of something that's purely in a product of something that's purely in terms of t and purely in terms of x. So in particular, it's 2t is the t function, and then cosine squared x. So you can just separate. So you'll end up getting, you just divide both sides by cosine squared x is equal to, and then you have a 2t, but then you multiply that by dt. So now that's successfully separated. You could just take the integral of both sides. And the right-hand side integral is a super easy integral. It's just t squared plus, I'll just put c2. Right, that's the antiderivative of 2t. What's the antiderivative of the left-hand side? This is not a hard one if you just know. It's what? So I'll just rewrite. Does anybody? So this is the same as secant squared x dx, right? That's not the antiderivative though. I'm just saying that, 1 over cosine squared is the same as secant squared, but do we know what yes. Yeah. So this is just tangent of x plus an integration constant c1. So you'll have both the c1 and c2 on each side, but you just shove it on one side. And so we're just solving for x. So I'll just shove the c1 to the other side. So then you'll get t squared plus c. I'm just going to write c without a subscript because I'm just combining the c1s and c2s. And then we're just still solving for x. So we'll just take the inverse tan of both sides. So it's going to be the solution x of t will equal t inverse of t squared plus c. So notice that I took the inverse tan of both sides. And so, of course, when I take the inverse tan of tan, that just gives me x. But then on the right-hand side, I took the inverse tan of the whole thing. So that's why the plus c is also in the inverse tan. Yes. We could just write it as x if you want. I guess I'm just trying. I'm just making it very explicit that it's a function of t, but you could just write x. It's fine. Is it downstairs? Oh, okay. They should do this at a different time. Okay. So this is the general solution, right? General solution because it has the integration constant c, so it's general solution. But in this problem, we also have an initial condition that they give us right here. So you can plug in the initial condition. What does the initial condition say? It says that x is equal to pi over 4 at t equals 0. Okay, so t equals 0 and x is equal to pi over 4. And you're trying to solve for the c after you plug in this initial condition. And you could plug it into this right here, but it doesn't, you could also plug it into here. This one looks nice to me because the c is already kind of out there and easier to work with. So if you plug in this initial condition, so I'll just say you're just doing this, you'll get tan of x is pi over 4. So this is pi over 4 equals t squared. Well, t is equal to 0. So that means it's going to be 0 squared plus c. So then you'll get that c is equal to tan of pi over 4, which is actually just 1, if you remember your unit circle. So this c is equal to 1. So that means that our actual solution to the initial value problem is x is equal to tan inverse of t squared plus 1. This 1 goes right where the c was. So I just chose to plug it into here. This is okay to plug it into where, I mean, this is a relationship. This is actually an implicit solution to x. You haven't solved for x explicitly, but it's a true statement that you have for in the process of solving this differential equation. So you could just plug in the initial condition into this because it's easier to get the c from there. And then you'll have your solution to the initial value problem. So I guess I could label this and say this is like an implicit solution to x. And these are like explicit solutions. I mean, generally, we want the explicit solution. Explicit means that you've just explicitly solved for x. Whereas here, this is also a true statement, but you haven't solved for x explicitly. So it's kind of an implicit solution for x. So that's the and this you might be tempted to think, okay, maybe you can say this is tan inverse of t squared plus tan inverse of c or tan inverse of 1, but you can't do that. There's no identity that says that you can split a sum. The inverse tan of a sum is not the sum of the inverse tans. It's similar to like the sine and cosine of a sum is not the same as just there is like an addition and subtraction formula, but it's more complicated. So that's the separable. That's the last separable. Now we're going to look at equations that are not separable. But even though it's not separable, I'm going to still keep it first order. So you just have first order means the highest derivative that shows up is a first derivative. And it this is like the classic general form of a first order differential equation. This f of t x used to have to be separable, means that it could be decomposed into a product of something purely in terms of t and purely in terms of x. But now we're gonna have a differential equation of a form like this. So if it's a form like this, then basically it means that we have f of x comma t is equal to f of t, and then you can subtract by p of t x. So this is a kind of right-hand side, right? F of t comma x, this is my right-hand side. And if you had a right-hand side that looked like this, and classically people like to take the term that has x, all the x's to be on one side. So you could have an equation that has my right-hand side looks like this, and then they like to write it in so-called standard form by putting all the terms on the right-hand side that have x to the left-hand side. You'll get this equation right here. And if you look at this, this actually is not separable in general. It could be separable if you, let's say, had f of t is equal to 0. So if you had f of t is equal to 0, then this would be negative p of t times x, and that's clearly a function that's purely in terms of t and x multiplied together. I guess if you had p of t equals 0, then that means the second term goes away and you just have f of t, and that's technically separable because it's just a function of t times a function of x that's equal to 1. But there are many f of t's and p of t's, basically any other types of f of t's and p of t's that will not make this separable. So we'll learn how to solve that in this section. A couple of other terms that I'm going to throw out here is this term called linear. Okay. So we all can appreciate that this is a first order differential equation because I'll just make a note that this is first order because the derivative is first order. But we are going to also only look at equations that are linear. So what does it mean for a differential equation to be linear? That means if the equation can be written as a linear polynomial in the dependent variable x. So x is the unknown solution. So I'll just underline the whole thing and say, x is our actual unknown. And if you can write your unknown and its derivatives as a linear polynomial in its in the unknown solution variable as well as its derivatives, then it's called a linear differential equation. So what does that mean? You have these derivative terms. So you have this dx over dt, and you also have this x term right here. I'll just do this and then move it. And those have to appear to a power of 1. So linear means to a power of 1. To a power of 2 is quadratic, cubic, we all know. So if you look at the x and its derivatives, they appear to a power of 1. It doesn't mean that your t's, this p of t and this f of t, they can be any general function of t. They don't have to be linear functions of t. It just means that your unknown solution, your solution variable x has to appear linearly, and its derivatives have to appear linearly. So what are some, let's see, so I'll just say that, your p of t and f of t, they can be whatever. So I'll just, let's just do this and say, okay, and then I'll make a note and say that these can be whatever you want, as long as they're functions of t. So for instance, they could be, these do not need to be linear. Well, they could be linear, but they do not need to be linear. So they could be something like t squared is fine. You could have square root of t is fine. You could have t over sine of t is fine. These are not linear. T to the negative 1 is also not linear. So these are all okay. What are examples of differential equations that are not linear? So those are called nonlinear ODEs. So if you had, for instance, dx over dt, and that was squared, and then you might have like I don't know, 3x is equal to 5 or something. That's not a linear differential equation. That's a nonlinear because you have a derivative that's been squared. Of course, you could have dx over dt plus 3 over x squared is equal to 4. This is also not a linear differential equation because you have 1 over x squared, right? And it turns out that things like this are also not linear. If you had x and dx over dt being multiplied together, they have to be linear polynomials in both the dependent and in both the x and its derivative. So 3x is equal to 5. So these are all nonlinear ODEs. Basically, anything that's not of this form is not so you have to have a dx over dt and an x right here. They both have to be, powers of 1, and they're not products. They're not multiplied together. So this last one right here, we have x and dx over dt multiplied together. That makes it nonlinear. So let's look at an example of a linear first order differential equation that is not separable. So if you were to look at this equation here, and let's say you want to try to separate this thing. Okay, so then you'll shove everything to the side. So you'll have dx over dt is equal to, let's say it's e raised to the t over t minus, okay, so this 1 over t times x is the same as x over t. And this would be separable only if you can get the right-hand side to be a product of two things where one is purely in terms of x and what's purely in terms of t. So you might think, okay, you can factor out a 1 over t, then you'll get e to the t minus x. But that's not going to help us if you're trying to use separation, right? Because you have 1 over t, so that looks like it's a function purely in terms of t. But e to the t minus x is not going to be possible to decompose into a product that's purely in terms of t and x. So this is not separable. So you can sit down and try as much as you want, but this is not going to separate. So you can't do like dividing everything by something that's purely in terms of x, and you can't get that to separate. So we can't do the stuff that we've been doing. So I'm gonna do a slight manipulation to this thing. It's gonna be something very clever, and you wouldn't probably realize to do this without you first knowing this technique. But I'm just gonna multiply everything by t. So I'm just take the whole thing and multiply by t. Okay, if you do that, you'll have the first term, the left-hand side is going to be t dx dt plus, of course, the t multiplies with the 1 over t, and so you just have x. And then when you multiply by t on the right-hand side, you just have e to the t. Okay, so I just multiplied everything by just t. And then I'm going to notice something very clever on the left-hand side. I'm going to claim that this left-hand side is the same as taking the derivative with respect to t of x times t. And then the right-hand side is just e to the t. Now let's just make sure that we understand that this is actually correct. Keep in mind that x is itself a function of t. So if I was gonna, let's go backwards. See, I make this claim here. Let's see if we can go backwards and see that these are actually equal to each other. Okay, so the idea is like, does this give me this? Okay, so this is like saying I need to take the derivative of x times t, but since x is a function of t, what differentiation rule do we need to do? The what rule? It's like, the basic stuff we know, like chain, well, not chain, well, chain rule could get involved, but it's a product of two things. So you might use the product of two things, so product rule. Right, so it's a product rule. You have x times t, but x is a function of t. X is also a function of t, right? Just keep in mind, x is a, we all know that x is a function of t. And all of these problems, x and in general is a function of t. So you have a function of t multiplied by t, that requires a product rule. So if you took the product rule of this, then do we get this? So it looks like you could say take the derivative of the first, which means dx over dt, times the second, which is t, plus you copy the first, which is x, times the derivative of t, which is 1. So this is actually the same. This is the same as this. Okay? But what does that buy us? That buys us something really, really nice, because what you could do is you can now just take the integral of both sides. So integral with respect to t of both sides. If I took the derivative of x times t, but then integrated it, what do you think the left-hand side would just be? X times t. It'll just undo itself. So I'll just, if you just thought of this as integrating, right? So you differentiate, but then you integrated it, right? So then you're just undoing, you took the derivative and then you're like going back again and say, well, never mind, just take the antiderivative of that thing back. Okay, you're back to xt, right? So that's the left-hand side. And of course, the right-hand side's antiderivative just e to the t. So you see that? So like, well, the part that you probably really confused is how in the world did I realize that I have to multiply by t? But if you just accept that I am able to see that, then we just multiply the left-hand side or the whole equation. So you can multiply the whole equation by something and you haven't changed it as long as you did it to both sides. And we did do it to both sides. And then this right-hand side ends up being the t derivative of this product, which you can find by using the product rule. You can convince yourself that these are the same things. And now I'm just going to take the integral of both sides. But now that this is actually the t derivative, a single t derivative of x times t, then it's like take the derivative of that. Okay, we don't know what that is, but then we're just going to take the antiderivative. So it just becomes xt. And then the right-hand side's antiderivative is e to the t. And then there's an integration constant. There's always an integration constant. And then you're just solving for x. So see how easy now x is going to be, because you just take the t and divide both sides by it. So it's going to be e to the t plus c divided by t. Again, the c is also divided by t. So I'll just say, do not just say e of t and then plus c. This is wrong. Right? This is wrong. The c came out first, and then you're multiplying everything by t. This makes it look like the c came after you multiplied everything by, or divided everything by t. So this is important that you get some minor amount of points off if this line isn't long enough. And didn't cover both of those. Okay, so this is actually the solution to this. This is your first example of a first order differential equation that is not separable. It's still, it's linear, and this class we're going to focus on linear equations, but it's not separable. Because if you try to shove this to the right-hand side and you get something like this, there's no way you can sit down after class and try as much as you want, but you're not going to be able to write this as a product, something in terms of just t and x. So how did I know to do this? So how did I know this? So how did I know this? So like, how did I know to multiply everything by t? That's the hard part. So the motivation was, I can multiply something to the left-hand side so that it'll look like the product of, it'll look like the t derivative of a product, a single t derivative of a product. So that's the thing, is can you stare at this and figure out that, oh, if I just multiply, or actually this right here, so this up here, if you stare at it and be like, oh, well, if I multiplied by t, then the left-hand side would end up being the t derivative of x times t. And then now I can just integrate that, and then it'll just be xt equals the integral of the right-hand side. So being able to stare at it and do that is not the preferred way for most people, because it requires brain power. You might want a systematic sort of formula, right? Like, can I just like, is there a way to not have to just notice what I need to multiply by? And so the book doesn't really do this, but like, it does actually give it as an exercise, I think. So I actually list it here. So there's actually these are all exercises that are actually in the back of the book. And then some of them are like, if you see this, that's supposed to be an emoji of me. So that's me. I wrote these problems. And then most of them I wrote, but this one's an exercise from the book. So the book says something like, they don't work it out. They just give it as an exercise at the end of this section. So you have a first order differential equation like this. To avoid having to guess, we need some method to compute sort of this factor we need to multiply to the whole equation. But the idea is we want to multiply by a factor that will make the left-hand side so that it can be written as a derivative of a product, a single t derivative of product. So we want to find some multiplicative factor u of t. In our previous example, our u of t ended up being just t, such that if I multiply this left-hand side, which is dx over dt over px, so I'll just make it very clear that this is the left-hand side, and I'm just going to multiply the left-hand side by u of t. You get this. If you did that, if you multiply by this factor u of t, you just distribute. And so u of t dx over dt, u of t times p of t times x. But we want this to end up being the derivative, a single t derivative of some product. So if you look at the first term, it looks like you have u of t times dx over dt. So I would say that this kind of looks like ux prime, right? What do we want this, oops, what do we want this this second term to be like, in order for it to be like the derivative of a product? Ux prime, you want this to be like u prime x. You want this to be like u prime x. Well, there's an x already here, so that's looking nice. So what do you want the u prime to be? You want u prime to be the rest of this thing. So I'll just write it like, oh, let's do this. So the u of t times p of t, you want that to be u prime t. If we can do that, then we have successfully made this be ux prime plus, because this is already ux prime. It's beautifully already done. This one almost looks like u prime x if we can just get ut times p of t to become u prime of t. And then, of course, that will make this the product rule on ux, right? So what's the punchline? We need to find u of t. So we're trying to find the thing that we're going to multiply this whole equation by, which is u of t. It turns out to be t in our previous example. We're into u of t such that this is true. This is true. So we'll just write that as u prime of t is equal to ut times p of t. We need this to be true. If we can find a u that will do that, then we can force this left-hand side to look like the t derivative of the product u times x. Okay, well, we just need to find u that does this. Well, it looks like u itself satisfies a differential equation, right? Because this is u prime is equal to, so you can rewrite this as du over dt is equal to u times p of t. I'm just rewriting it like this because we're used to seeing it like this. And guess what? This is actually separable. So how do we separate this? So I'll just come down here and say, okay, we're just going to have u divided by u, which is divide both sides by this u, and then equals p of t times dt, and multiply both sides by dt. And now we can integrate both sides. And if you do that, you'll just have ln of absolute value of u is equal to, that's the left-hand side, but unfortunately on the right-hand side, we have no idea. Well, p of t could be anything, so we're just going to leave it. T dt. Of course, when you took the antiderivative of the left-hand side, you got a plus c that showed up, so I'm just shoving that to this side. And then you can take the exponential of both sides. So you get absolute value of u is equal to e raised to p of t dt plus c. And then we can pull you can write the factors out and then also do plus or minus. So let me just try to shove this here. So it becomes u is equal to plus or minus e raised to the c, e raised to the p of t dt. And then we can rename this as another arbitrary constant c. And so therefore, the u of t, the factor we need to multiply both sides by, in order for us to successfully make the left-hand side look like the product of the derivative of a product, is just c times e raised to the integral of p of t dt. So we've successfully found what the formula for the thing we need to multiply both sides by. And this thing actually has a special name. It's called the integrating factor. I guess it's called the integrating factor probably because it allows us to be able to eventually take the integral of the whole equation to be able to solve for x. And this is the integrating factor. So the yes. So that's good. Yeah. So there is a c here that shows up just because this is the differential equation for u, and of course there's going to be some c that shows up for this. So it turns out that there are infinitely many integrating factors that would work. So in the previous example, I chose t, but 2t would have worked actually, or 3t would have also worked. I mean, they're all just a constant multiple of it. So you are free to choose the c, and in fact, the common practice is to just so you just need one integrating factor that works. You don't need like to do it. There's infinitely many you can choose from, so might as well choose the easy one. So it's very common for people to choose c is equal to 1, because then and the book will have this and say, okay, the integrating factor, the thing we're going to multiply the whole equation by, is just e raised to the integral of p of t dt, where they've set the c to equal 1. And so you're free to do that. And that's the integrating factor. Let's just go backwards and see that we actually get that up here. So let's so it's how do we derive this integrating factor? We derived it with given our equation written in standard form like this. So dx over dt p of tx equals f of t. And this is important because the integrating factor is in the formula for the integrating factor, you have e to the integral of p of t dt. So you have to identify what is the p of t for your equation. And you have to write it in this form. And you also have to remember that there's a dx over dt that doesn't have anything in front of it. So if there was something in front, then you want to also divide by it so that it really is dx over dt multiplied by 1, and then everything else in this form. This is already the case here. So you just have that this is our p of t. And so if you wanted to find the integrating factor for this, then the formula was u is equal to e raised to the p of t dt, which is e integrated with 1 over, so it's going to be dt over t. Or maybe I'll just make it very clear that write it in blue. So it's going to be 1 over t and then dt. And what's the antiderivative of 1 over t? It's just ln of absolute value of t. And then I guess you can say plus c. But we know that we only need one integrating factor. And so I'm just going to make our life easy and just say, why don't we choose c is equal to 0? We just need one that works. So you just have e to the ln of absolute value of t. And the e and the ln's cancel, so you have absolute value of t. And it's not quite the same as what we had here. So I don't have time, I guess. So I'll justify why we can drop the absolute value. Turns out that we can drop the absolute value. You know, I think I've justified that we can choose our integration constant c to be 1 or 0 or whatever you want, because you just need one that works. But the absolute value might not be clear, but it's not hard to show that that could be dropped. Sorry that I was a little bit late. We could have been able to finish it, but I guess I won't be able to. But we'll be able to do that, and and next time we'll be able to solve another example or two that uses this integrating factor method. Yeah. Yeah. See ya.